AI models are mathematical models. The only input that they understand are numbers. Then, in that case, how do these models understand natural language? How are these Gen AI models so good at generating the right response to our natural language inputs? AI models represent the words in our input text in the form of embeddings. Embeddings are dense vector representations of words, phrases, or sentences in a continuous vector space where words that are similar in meaning are close together in this vector space. Embeddings are thus numeric representations of words that capture semantic and syntactic relationships between words. It's these embeddings that enable machine learning models to process and understand natural language more effectively. Now, you can generate embedding representations for words, but you can also generate them for images and video. Generating these embedding representations are useful in many situations. For example, in semantic search. With embeddings, you can search text ranked by semantic similarity. You can use word embeddings or image or video embeddings for classification problems. This will allow you to classify or categorize items whose attributes are similar. Embeddings can be used for other cases as well, such as clustering or outlier detection. In this demo, we'll use the Embeddings API that Vertex AI has to offer in order to generate embeddings for words as well as images. And we'll see how we can compute the similarity between these embedding representations. Go ahead and set up the imports as you see here. And again, we'll initialize our Vertex AI client as before, vertexai.init. Google supports several embedding models. For example, any model with the suffix gecko, these are multilingual models. Now, the model that I've picked to generate embeddings is the text embedding 005, which is an embedding model specifically for the English language. I'm going to call text embedding model from pre-trained to load in this model into our current program. If my explanation of embeddings previously was rather abstract, well, this will make it more concrete. When generative AI models work with the words in our input sentences, they don't actually see the text, they only see the embedding representation of that word. And the embedding is just a dense vector. Now I call model.getEmbeddings and I've passed in the input dog. And I'm going to print out the embedding representation of this dog as per this model. Observe the dense vector representation of dog that captures the meaning and syntactic relationships of the word dog with other words in the English language. One important thing to note, different embedding models have their own embeddings for the different words. So let's go ahead and print the type of this embedding that we've generated using the Vertex AI models. You can see the embedding is a list. It's a list of numeric values. So let's go ahead and access the values within the embedding. And this is actually the dense vector embedding representation of the word dog. Now you can see a large number of elements here in this vector. And if you compute the length of this vector, you'll know how many individual elements are used to represent dog. This model uses a dimensionality of 768 to represent words. Different models can have different embedding dimensionality. Now let's get the embedding representation of the word puppy. So I call model.getEmbeddings, pass in the word puppy, and I store the vector representing puppy in the embedding puppy variable. I mentioned the fact that embeddings are not random dense vector representations, but they capture the semantic meaning of the word. And I'll now prove that to you. Here I've set up a helper function to compute the cosine similarity between two vectors. Cosine similarity is used to measure how similar two non-zero vectors are by calculating the cosine of the angle between them. Values range from -1 to 1. A cosine similarity value of 1 indicates identical vectors, 0 indicates orthogonal vectors at right angles. The vectors are not similar at all, and -1 indicates opposite vectors. Cosine similarity is used in NLP to compare text embeddings. The cosine similarity function takes in two embeddings, embeddings A and embedding B, and on lines 5 and 6, we perform a mathematical computation to compute the cosine of the angle between the two vectors. This mathematical computation divides the dot product of the two vectors by the product of the magnitudes of the two vectors. The norm calculation computes the magnitude of the individual vectors. You don't really need to know how this math for cosine similarity calculation came about. All you have to understand is the intuition behind cosine similarity. Now I have the embedding for dog and the embedding for puppy. Let's see how similar they are. Notice they have a cosine similarity score of 0.87, meaning these two words are very similar. And we know that indeed they are. Cosine similarity values close to 1 indicate a high degree of similarity. Now let's generate the embeddings for two more words. I'm going to generate the embedding for the word computer and store that in embedding computer. And then I'm going to generate the embedding for the word laptop and store that in embedding laptop. Let's now compute the cosine similarity between these two words, embedding computer and embedding laptop. And you can see they are very similar as well, with a similarity value of 0.81. However, we know that computers and dogs are very different. Let's compute the cosine similarity between embedding computer and embedding dog to see whether this is captured in the embedding representation. And indeed it is. You can see that the similarity score is just 0.63. Now that we've understood how cosine similarity can be used to find words that are similar, let's see how we would use embeddings for semantic search. Just a very simple example. I've set up a helper function here called getEmbedding that takes in a word as an input argument. I then call model.getEmbedding to get the embedding representations, and I return the dense vector representation for this word. I index into the embedding and return the values. In my current working directory, I have a subfolder called CSV file, and within that I have the word collection.csv file. This is basically a list of around 100 words that I asked a generative AI models to generate for me, and these words pertain to different topics. I use pandas to read in the CSV file and I print out a sample, and you can see that these are words which are completely different. They relate to different topics, but some words are related to one another. Now that we've read in this bunch of words, I'm going to add a new column to the data frame which holds the embedding representation of each word. On line 1, I apply the lambda function to generate the embedding for each word to the words column. This lambda function will generate the embeddings for all words in our words column in our data frame, and it will store the result in the embedding column. Now, after this is done, let's take a look at our data frame, and you can see that along with the words themselves, we now have an embedding representation for each of these words. These embedding representations capture the semantic meaning of that word and the relationship that that word has with other words in the English language. Generating the embeddings took about 2 to 3 minutes on my machine, so I'm just going to go ahead and save the words along with the embeddings as a CSV file on my local machine. You can always reread this file in if you don't want to regenerate the embeddings. This is just for backup. Now let's see how you would actually perform semantic text search. I'm going to use the Python input function to input a search term, a term that I'm looking for. This need not be a term that's actually present in my word collection. We'll use the embedding representation of this term to find other terms that are similar to this. The first search term that I've entered here is the word bagel. In order to find words that are similar to the word bagel, I'm going to generate the embedding representation for the search word, which happens to be bagel at this point in time. So this is the embedding representation for the word bagel, and this is what I'm going to use to find other words that are similar to bagel. I'm curious to find those words that are most similar to my search term bagel. And in order to do that, I'm going to compute the cosine similarity of our search term bagel with every other word in my collection. And that's what the lambda on line 2 does. I compute the cosine similarity of x with the search term vector. X here is the embedding representation of the words that I have in my data frame. I store this cosine similarity metric in a new column in the data frame called similarities. Now, if you look at the words BF, we should have the original words, the embedding representation for each of those words, and the similarity of that word computed against the search term bagel. Semantic search is now very, very easy. Higher the cosine similarity score between the search term bagel and the other words in our list, greater the similarity between the words. So all I have to do is sort the words data frame on the similarities column in the descending order. That's what this code does, and I print out the top 20 most similar words. Observe the word that was most similar to bagel is bagel itself. The similarity score of a word with itself is 1 because the words are identical. And the other words at the top here are different kinds of bread. Baguette is the closest, then challah, then pretzels, then brioche, then focaccia, flatbread, and so on. So you get a large number of semantically similar bread options. And at the very bottom, notice you have New York. Well, bagels are intimately associated with New York, and it makes sense to have New York in there as well. Now that you've understood the mechanics of semantic search, you can try this with a few more search terms. Let's try another search word, and this time I'm going to type in the word cold. Now, first thing we do is compute the search term vector, that is the vector representation of the word cold. We then compute the similarity score of all other words in our data frame with the search term cold. The similarities column now contains the cosine similarity against the new search term. Let me go ahead, sort the data frame based on similarities. And if you look at the results, you can see that cold is not present in my data frame. So it's not a word that's present in my data, but the closest, most similar word is frost, then we have snow, then we have overcast. If you scroll down, you'll see other words here that are associated with cold but may not mean cold, such as skiing, hockey, and skating. You have to admit that embeddings do a pretty good job of capturing the semantic meaning of a word. Let's try this once again, this time with a different word. This time I put in Statue of Liberty. Let's set up the embedding representation of this phrase. It's not a single word, it's a phrase. You can get embeddings for phrases and sentences as well, and images too, as we'll see in a bit. I'll now compute the similarity of all other words to the Statue of Liberty. Let's sort our word collection by how similar the words are to Statue of Liberty. And even though Statue of Liberty is not present in our list, the closest option is the Eiffel Tower. The Statue of Liberty is an important historical monument, as is the Eiffel Tower. Liberty Bell is close. New York is close because the Statue of Liberty is in New York. Let's try this one last time with the word igloo. Now, the way I type in the word igloo, notice the lowercase I. Now I have the word igloo in my search collection, but it has the uppercase I. I'm going to go ahead and generate the embedding for igloo. Next, we compute the cosine similarity of all the other words with the word igloo. Once we have the cosine similarity metrics for all words in our data frame, let's sort the data frame in the descending order of similarity scores, and we'll see what words are the most similar to igloo. Notice here that the most similar word is the word igloo itself, but its similarity score is 0.993 and not 1 because this igloo has the uppercase I, whereas our search term had igloo with a lowercase I. The embedding representation in this model is a little different based on whether you use uppercase or lowercase for your characters. Just something to keep in mind if you plan to integrate this into your application. You can also use word embeddings in classification and clustering problems. In this next example, I'll show you how you can use word embeddings to cluster words together. Words that are similar should be part of the same cluster. We've already generated embeddings for all of the words in our words DF. I'm just going to use those words and those embeddings. Now, the first thing I do is set up an embedding matrix using np.vstack. This basically creates a matrix of all of the word embeddings, where the embeddings for an individual word are the rows in that matrix. So np.vstack will vertically stack the word embeddings for every word. If you look at the shape of the embedding matrix, you can see that it's 130 by 768. There are 130 words in our collection, and 768 is the dimensionality of the embedding for each word. We now have a single matrix that holds the embedding representations of all of the words in our collection. Now, in order to perform clustering on this data, we'll install the scikit-learn library using pip install scikit-learn. Scikit-learn, as you likely already know, is a great framework for building traditional machine learning models, such as linear logistic regression, random forest decision trees, and of course, k-means clustering. Now, we are going to be performing clustering on our word vectors using the k-means clustering algorithm. K-means clustering will group our data points into k distinct clusters based on how similar the data points are. This will allow us to identify patterns or structure within our dataset. In the k-means model, you have to specify how many clusters you want to find in your data upfront. On line 3, you can see I've set n clusters to 6. I initialize the k-means model on line 5. I specify n clusters equal to n clusters, that is 6. The init method sets the initialization method for the cluster centroids. K-means plus plus is a smart initialization technique that helps select initial centroids to speed up the convergence of the algorithm and improve clustering quality. I've set random state to 42. If you use the same value, this will ensure that you can reproduce the same results that I'm seeing on screen. Ninit1 specifies the number of times the k-means algorithm will run with different centroid seeds. I've asked the algorithm to run just once. On line 7, I train the clustering model by calling k-means.fit and passing in the embedding matrix. This will cluster the word vector representations that are present in the embedding matrix. Once clustering is complete, every data point, that is a row in the embedding matrix, will be assigned a cluster label. I access those labels on line 9. On line 11, I update the words data frame so that it now has the cluster labels as assigned by k-means clustering. Let's take a look at the result here. Observe now, every word has a cluster label assigned, the cluster column at the very right. Now, I'd really like to visualize what words belong to what cluster. Unfortunately, you can't do this as is. That's because each word vector is represented using 768 dimensions, that is the length of the embedding, and we can't visualize 768 dimensions in our two-dimensional space. Dimensionality reduction is a technique that is used to visualize high-dimensional data, such as our embedding representations, in two-dimensional or three-dimensional space, while preserving the structure and relationship between the data points. The TSNE algorithm that I've imported on line 1 stands for T-distributed stochastic neighbor embedding and is a dimensionality reduction algorithm. On line 4, I get the predicted labels for each word vector in my embedding matrix that's stored in the labels variable. And then on line 6, I instantiate the TSNE model. N components equal to 2 indicates that I want to reduce our high dimensionality vector into two-dimensional space. The perplexity parameter that we pass in balances the local and global aspects of data, and it affects how the algorithm calculates similarity between points. Random state is for reproducible results. Init equal to random specifies the initialization of the reduced dimensional space, this is random, and the learning rate 200 controls the rate at which TSNE optimizes the embedding. We then call TSNE fit transform on the embedding matrix to get the word vector representations in two dimensions, that is the viz.dims2. The rest of the code on lines 10 through 17 basically plots a scatter plot where each data point represents a word. We'll have the actual word labels associated with each word so that we know what word each data point represents, and the data points will be colored based on the cluster that they belong to. And here is what our word vectors reduced to two dimensions look like. Notice that similar words are in the same color, indicating that they belong to the same cluster. On the top left, we have all of the breads. At the bottom right, we have tower, castle, duplex, different kinds of homes. You can see the data points of some clusters are close together, as in the top right. These are clusters related to historical monuments, Stonehenge, Sphinx, pyramids, and cities, Delhi, Mumbai, Sydney, etc. But this visualization in 2D makes it very clear that words that are similar are close together in space. Just like you can generate embeddings for text data, it's possible to generate embeddings for images and videos as well. In this example, I'll show you how you can generate embeddings for images. Here I am on the Google Cloud Console within buckets. I have the Looney LLM bucket that we had created earlier. Here in this bucket, I'm going to upload some images and we'll generate some embeddings for those images. I'm going to create a new folder called Embeddings. And here in this folder, I'm going to upload some image files that I have on my local machine. All of these images have been downloaded from pexels.com. Let's take a look at what these 4 images look like, and then we'll generate embeddings for these images. Here is the dog 1, which is a cute Labrador. Here is dog 2, which is a dog, but it's a pug and it's black in color rather than the Labrador white. Plane 1 here is an image of a passenger plane. And then I have another plane image, but it's a very different kind of plane. It's clearly a fighter jet. You cannot use the same model that we used in the previous video for text embeddings. This is going to be a different model. And notice how we load it as well. The name of the model is multimodal embedding at 001. And I load it by calling multimodal embedding model dot from pre-trained. We'll have this model generate embeddings from the images stored in our Looney LLM bucket. Next, I'll set up references to the 2 image files that we have, the 2 dog image files. I call image.load from file and reference these images in our Looney LLM bucket within the embeddings folder. So I get 2 image objects, image dog 1 and image dog 2. Now these multimodal embedding models can generate embeddings not only for images but also for any contextual text that you associate with images. Notice here I call model.getEmbeddings. On line 2, I pass in a reference to the image dog 1. On line 3, I specify some contextual text for the image. This is a Labrador. Next, on line 4, I specify the dimensionality of the embedding vector that I'd like to use for my image representations as well as the contextual text representations. Now, this particular model that we've used, the highest possible dimensionality is 1408. This is the default dimensionality of embeddings returned by this model. However, it's also possible to specify lower dimension embeddings of length 128, 256 or 512 for text and image data. Remember, higher dimensionality embeddings will capture more nuance in the text and image. Lower dimensionality vectors will capture less nuance but are more storage optimized. Now that we have the embedding representation for dog 1, let's take a look at the image embedding. And here you can see the dense vector representation for the image. If you were to compute the length of this image embedding, you will see that it's equal to 1408. That's the dimensionality that we had specified. We had specified some contextual text along with the image, and the text embedding property will give you the embedding representation of the contextual text, the word Labrador. The length of this text embedding will also be equal to 1408. Now let's get the embedding representation of another image that we have, the image of a pug, that is image dog 2, contextual text says pug. Make sure you specify the same dimension for the embedding because otherwise we won't be able to compare these 2 vectors. Now let me go ahead and get a reference to the images of the 2 planes. In both cases, I use image.load from file once again. If you remember, plane 1 was a passenger plane, plane 2 was a fighter jet. Now I'll get the embedding for plane 1. The contextual text says airplane and dimension is 1408. I do the same for plane 2. The contextual text says jet. Now that we have all of the embeddings that we need, let's compute the cosine similarity scores between pairs of embeddings. I'm curious to see whether the images of the 2 dogs have a high cosine similarity score because both of them are dogs, but the dogs themselves are very different. And you can see that it's pretty high, 0.745. Remember, 1 means the 2 images are identical. The contextual text associated with the 2 images was Labrador and pug respectively. I'll now compute the cosine similarity of the contextual text, and you can see this is really high, 0.815. Pug and Labrador are clearly very similar. Let's compute the cosine similarity of the images of the 2 planes. Notice I use the image embedding for comparison. And you can see that even though they're both planes, they're different types of planes. So their similarity metric is not that high. It's only about 0.6. Let's compare the text embeddings, that is the contextual text that says airplane and jet. That's much higher, 0.88. The images are much more different than the contextual text would indicate. Now, let's try two different things. We'll compare the image embedding of a dog with the image embedding of a plane, and you can see that the similarity score here is just 0.46. Let's discuss some other bits of useful functionality when you work with text generation models, grounding models, and using function calls. Now, this you can think of as an introduction to what it means to ground a model. We'll talk about grounding and how it compares with retrieval augmented generation and fine tuning once again later on in this learning path. At this point, all of us have some experience with generative AI models, and we know that their responses can often be prone to hallucinations. Grounding involves integrating the model with trusted APIs, proprietary databases, or live data streams, allowing it to fetch specific and accurate information as needed. You connect the model to verified external data sources. Now, unlike static pre trained models, grounded models can adapt to changes in real time data, making them ideal for tasks requiring up to date information such as market trends or news summaries. Models are thus integrated with dynamic knowledge. When you use grounding with Gemini models, the system evaluates whether a prompt requires up to date or specialized information. If the model's existing knowledge suffices, grounding is bypassed. Otherwise, data is retrieved from sources like Google search, or you can connect the model to your proprietary data as well. Another way to allow your model to access real time data is via external function calls. This is where the Gemini model is allowed to interact with APIs or external systems. External function calls enable an AI model to invoke external APIs or services during a session to fetch real time data or to perform specific operations beyond its built in capabilities. The purpose of these is to allow the AI to extend its functionality by interacting with external systems, such as retrieving current weather data, executing financial calculations, or accessing custom business logic. While using function calling, you need to specify the different functions that are available for the model to invoke as needed with the right arguments. Declaring these function calls and making them available to the model is important so that the model knows what function to invoke. Next, once you have the model which has these functions available, let's say you specify a prompt that needs information from one of these function calls. The model will realize that, well, it doesn't have the information on its own. Can any of the functions configured provide this information? If yes, the model's response will include the function that needs to be invoked and with what parameters. Please note that at this point in time, the model does not directly invoke the external API to make function calls. These external function calls may require additional authentication not available to the model. External function calling is very useful for applications like dynamic personalization, real time updates, database lookups, or executing specific tasks tied to user queries. Let's discuss step by step how the model tells you what function call to invoke. When you specify your input prompt to the model identifies that the user prompt requires external data or processing. The model will only know of this if you declare what function APIs are available to the model in a specified format and you integrate that as a part of the model. The model does not know of any and all APIs that exist in the world. So these are APIs that you know are available and that you can call and you make them available to the model. The functions that the model knows to call is guided by predefined rules, keywords, or conditions that we as developers set during the model's integration. Developers, by declaring functions, predefine the mappings that associate specific types of requests with the relevant APIs. You'll then send your prompt to the model, and based on your prompt, the model will determine what API it needs to invoke and with what parameters. For instance, if you have a financial query that may be routed to a stock market API that you've configured, or a location based query could invoke a map services API. Both of these APIs you have to have configured upfront. The model's response will include the API that you need to invoke and what parameters you should use to invoke that API. So then all you have to do while parsing this response is make the actual API call. And this is important. The model will not make the API call for you. Remember that making an API call will involve authentication and authorization, and the model simply will not have the information to be able to make the API call correctly. It's up to you as the developer to parse the model's response, make the API call, and get the response from the API. The cool thing is, after getting the response from the API, you can pass the API response back to the model, and the model, because it has the context of your original prompt, the API that it suggested you call, when it sees the API response, will give you a response in natural language text, easy for the user to understand. In order to really cement our understanding of how function calling works, here is a big picture overview with different components involved. I know there's a lot going on here, but I'll break this down to make this really simple for you. On the very left, we have the user. The user interacts with an application that you as a developer have built. Observe that it is your application that's interacting with the large language model. The user does not interact directly with the model here because there is a function call that your application has to make. Let's go step by step here. The user interacts with your application, and it's your application that knows how to call the real-time API. Now, your application is what will send back the final response to the user, complete with details from the API. Very, very important to note here is that the user is not directly interacting with the large language model. Instead, it's your application receiving the user prompt and returning the response to the user. Maybe your application is some kind of financial application and it requires information from a real-time stock ticker API. Now, that is the function call that your application has to make. It's your application that will make the API request to the real-time stock ticker API and get the response from the API. Your application has the right authentication, maybe the API keys or tokens that are needed to make a request to the API and get the response. However, your application may not understand the natural language query of the user, nor can your application know how to call that particular API. This is where the large language model comes in. As an application developer, you know what functions are available and what APIs are available to get the information the user needs. When the application receives the user prompt, it will send the user prompt along with the functions that the model can invoke to the large language model, that is, to Gemini. It's Gemini that's responsible for parsing the user's prompt and extracting the user's intent. Gemini will translate the user's intent to the right function call with the right parameters. Notice that Gemini not only specifies what function to invoke, but also what parameters to use to invoke that function. Once the application gets the model's response with the API to call and the parameters to use, well, the application makes the API call by itself. Once the application gets the response from the API call, the application once again sends a request to the large language model. And this additional request will contain the response from the API, the real world data from the API. The model has the context of the original user prompt, and now when it's given the response from the API, can extract the relevant details based on the user's prompt and send back a natural language response to the application that is then sent back to the user. It's important to note that while the user sends one prompt and gets one response, the application itself has multiple interactions with Gemini. First, to send the user prompt and know what API has to be called. And then, after calling the API and getting the response, the application once again sends the response from the API to the model to get a natural language response, which it then sends back to the user. At this point in time, the models that support external function calls include the Gemini 1.Pro model, the Gemini 1.5 Flash model, and the Gemini 1.5 Pro model. Function calling addresses an important drawback of large language models. that of accessing live external data. Large language models are frozen after training, which means that once they've been trained on data, the knowledge that they have often tends to be stale. Also, large language models by themselves can't query or modify external data. Function calling or tool use allows the model to use external tools such as APIs and functions in order to return responses to users. When you use function calling, along with specifying the prompt to the LLM, you also provide the model with a set of tools that it can use to respond to your prompt. You could provide it a function, say get stock price, that takes in an input ticker parameter. And if your query is about, say, the current stock price of Google stock or Tesla's stock, the model can return a response where it provides structured data output that includes the function to call and the parameter values to use. It's important to note that the model does not call the function directly. The model's response will include the function to call and the parameters to provide. Let's see how we can include the function calling as a tool to our Gemini model in order to get real live data. Set up the imports and then go ahead and call Vertex AI.init to initialize the client libraries. You should be able to use any recent model for function calling. I'm going to use the Gemini 1.5 Flash 002 model. The first example that we're going to look at here is a toy example that we'll use to understand how function calling works with Gemini. I'm going to define an API that the function can call to search for events, but this is not a real API. You'll be able to evaluate the model's response where it specifies the function that you'll have to call in order to get your information. In order for a model to know about a function, you must declare the function using a function declaration. The function declaration essentially tells the model that this is a function that's available that the model can use to get the response that it needs. The model will not call the function directly, but instead will give you a response indicating what function should be called and with what parameters. Now, here my function name is search events, and I have a function declaration on lines 3 through 14. The function declaration takes in a function name, the description, and the parameters used to call the function. Now, this parameter specification on lines 6 through 13 uses the Open API specification. Open API is a specification for designing, documenting, and describing RESTful APIs in a standardized format, typically using JSON as we've done here or YAML. OpenAPI allows developers to define API endpoints, request response structures, and parameters. This OpenAPI specification indicates that this function takes in an object as an input argument, and keyword and state code are the two properties of the object. And on line 12, you can see both of those are required properties. I'm now going to configure the prompt that I send the model, and I'll define the prompt using a content object. The content object allows me to specify the role, that is user, and the different parts of the prompt. My prompt just contains simple text. I've asked the model for some music events in California. This is clearly live data that a model by itself will not have information about. Next, let's set up our function as a tool. This event tool references our search events function, the function declaration that we set up earlier. This is a tool that we'll pass on to the model when we make a request using our prompt. I now call model.generateContent, pass in my user prompt content object, specify a generation config and set temperature to 0, so the answer is very deterministic and not creative. And I use the tool's input argument to pass in the event tool that knows about our external function. And here is the response from the model. The response from the model is basically the function call that you see on screen. There is no other natural language response from the model. Let's extract this function call and examine exactly what it does. So from the response candidates, I extract the function call and I print that out to screen. And this is the function the model is asking us to invoke in order to get an answer to our question. It gives us not only the function name, but also the arguments that we need to pass to the function. So call the search events function, pass in the state code as California, CA, and the keyword field should have the value music. Observe that the model does not actually make the function call to give you the results. It cannot, because the function might require additional API keys, etc., that the model doesn't know about. If you're using this in your product, it's very easy to build a wrapper around this model's response and actually make the function call yourself. Let me show you the content of the entire response from the model. So response candidates index position 0, content. This is the content of the response. The role is model, and then we have the function call. Because the model does not actually make the external function call, I'm going to go ahead and simulate an API response from the external search events function. This is the simulated API response. I'm going to be using it in a prompt in just a bit. This simulated API response gives us a concert in New York City, a rock festival in LA, and a literature fest in San Francisco. I'm going to store the response that we got from the previous call to the model, the actual content of the response that we looked at earlier, in this variable called response function call. I'm going to be using this in a bit as well. You'll see how all of this comes together. I'm now going to put all of this together and send a prompt to the model with a series of messages. On line 4, we have the original prompt. This original prompt is where we ask the model to give us some music events in California. On line 7, I have the model's response. This is the model's response where it invokes the search events function with the right parameters, searching for music in California. And then on lines 10 through 19, I have the content object, that is the API response that we want the model to use. This is the simulated API response where we defined 3 events, one in New York, one in LA, and one in San Francisco. I use part.from function response to indicate that this is an API response. I specify the same function name, and the response content contains the API response. Then finally on line 21, I pass the same event tool to the model in case it needs to use that again. You'll see that the model is able to parse all of this. It'll see the original prompt, our user prompt. It'll look at the API response and it'll give you an answer in natural language about what music festivals are available in California. Notice it says, I found some music events for you in California. There is a rock festival in Los Angeles. There may be other events as well, but this is what I could find based on my current knowledge. It used the API response to point us to the right festival that met our request. Let's specify a slightly different user prompt. Are there any events related to books anywhere in California? Now, our API response contains a literature fest in San Francisco. I want to see if the model is able to identify this. I have the same series of prompts that I passed to the model. The new user prompt on line 4, the previous response function call. This is the model's response indicating what function to invoke. Then finally on lines 10 through 19, I have the API response that we want the model to use. Let's see what the model has to say. The model says there's at least one event related to literature in San Francisco. I found this information by searching for events with the keyword books. But I used music in my search because there was no information on how to search for books. That's because our response function call on line 7 searched for music, not books. And the model also tells me there may be more events if a more targeted search were possible. The next demo on function calling is going to be a little more interesting because we're going to use a real-world API. This is the Ticketmaster API. Before we look at the actual demo, I should tell you that Google has a number of great example notebooks for function calling, showing functionality beyond what we're going to look at in this demo. I found these notebooks a great reference, especially for all of the utility functions to help parse function calls from model responses. Ticketmaster offers a free-to-use API that you can use to search for events across different countries. Now I've gone to developer.ticketmaster.com/products and docs/APIs getting started. Here you'll find an option to get your API key, but before that, you'll need to create an account and log in. All of this is absolutely free. So you can scroll down here and click on create an account. Fill in all of the details on this page and agree with the terms and conditions at the very bottom. This will allow you to create a new account. And once you've created a new account, you can click on Get API Key and get an API key that you'll use. Make sure you specify a valid email address because you'll need to verify that email address. Here is the email that I got from Ticketmaster. Click on that link to verify your email. This is a one-time login for Alice. I'm going to go ahead and log in. This will take you to a profile page where you can then create a password that you'll then use to log in to your Ticketmaster account. So I've created a new password, confirm the password, and I'm going to click on Save. You've now created a developer account on Ticketmaster. Head over to My Apps, and here you'll find an API key has been automatically generated for you. You'll need to scroll down here, observe that a new Alice app has been created. Expand this and notice the consumer key there. That's the key that we're going to be using. Go ahead and copy this over. We'll be pasting this into our code. This is the API key that we'll use to access the Ticketmaster API. Now I'm going to head back to the original Getting Started page on Ticketmaster to see what APIs are available. So here you can see that we have a Discovery API which will allow us access to global events. So events, attractions, and venues across the world. This is the API to which we're going to make calls. I'll show you what APIs we use exactly once we switch over to the code, but this is the page that I use to get the details of those APIs. We are now ready to see function calling in action using the Ticketmaster API. Set up the API key in the Ticketmaster API key variable. And now I'm going to declare 3 separate functions. The first function declaration is on lines 1 through 26, and this is the search events function. You can see the description: search for events based on keywords, location, or category. On lines 4 through 23, I have the open API specification for the parameters that we need to call the function. We have to pass the API an object with a keyword of type string, a country code of type string, a classification name of type string. This is a category of event like music, sports, rock concert. And then there is a DMA ID, a designated market area ID for event location. The only required properties are keyword and country code. Now, this first function searches for events. The second function searches for venues. Name and description: search venues and search for venues by location. The parameters to pass to this function is on lines 31 through 42. We need a city and a country code, and both of these properties are required. Now, the third function declaration is on lines 47 through 68. This is the search attractions function, which searches for attractions based on keywords and location. The 3 possible properties are keyword, country code, and city, and only keyword and country code are required while calling this function. The next step is to set up a tool that our model can use, and we'll configure these 3 function declaration. The Ticketmaster Insights tool can call search events, search venues, and search attractions. In this example, we are actually going to invoke the Ticketmaster API. The model is going to tell us what function to call and with what keywords, and we're going to use that information to invoke the real API. So I'm going to set up a bunch of helper functions for that. I have the fetch events helper function, which takes in the model response, that is the content input argument. The actual URL to call is specified on line 2, and on lines 4 through 10, I have the query parameters that you need to pass to the Ticketmaster API. The remaining keys, keyword, country code, classification name, and DMA ID, come from the corresponding fields in the content object passed into fetch events. Remember, this content object is the response from the model, the function to call. On line 12, we use the request library to make a GET request to the URL with the parameters that we've configured, and we return the response JSON on line 13. The fetch venues helper function makes an API call to retrieve venues from the Ticketmaster API. We have the URL to hit on line 16 and the parameters to send the URL on lines 18 through 22. Again, other than the API key, the other parameters come from the content passed into fetch venues. The content here is the response from the model about what function to invoke and the parameters to use to invoke the function. On lines 24 and 25, we make the GET request to the URL and return the response JSON. And finally, the third helper function, fetch attractions is set up in the same way. The URL that we hit is different, the parameters are a little different, but all of the parameters come from the content passed in as an input argument, and we return the JSON response from the API. Next, I'll set up a dictionary that maps the names of each of the functions, search events, search venues, and search attractions, to the utility function that actually makes the function call to the right API. We are getting very close to making real API requests. Instantiate a generative model. I'm using Gemini 1.5 Pro 002. Set temperature to 0 so that we get deterministic responses. And tools points to the Ticketmaster Insights tool, which has the 3 configured function declarations. I'm now going to interact with a chat session so that I can ask follow-up questions about all of the events that I'm interested in. Go ahead and start the chat. I'll now define a helper function that will send a message to our model and parse the response from the model and extract the functions that need to be invoked. We'll then make the actual API call to get the real responses from the Ticketmaster API. Send chat message takes in a prompt as an input argument. This is the user's request for events in a certain country. We'll display the prompt on line 3 and then we'll add to that prompt. On lines 4 through 7, we add to the prompt. We ask the model to give a concise high-level summary and only use the information that the model learns from the API responses. And on line 8, we send a message to the model. The model's response will contain a number of functions that need to be called. We'll set function calling in process to true to start off with, and so long as this is true, we'll run a while loop that starts on line 12. Now, if the response contains something in its parts on line 14, we extract the function call that's present in the response. Otherwise, we set function call to none on line 16. On line 18, we check whether the model has suggested a function call and whether the name of the function to invoke is present in our function handler dictionary. If yes, that's a Ticketmaster function that we are going to invoke. On line 22, we print out the name of the function that we are going to invoke, and on line 24, we get the parameters that our model response has suggested that we should use to call the function. On line 26, we print out the parameters which we are going to use when we make the API call. On line 29, we make the actual function call. We look up the function handler dictionary. This maps the function name to the utility function that invokes the correct API, and we parse in the parameters that Gemini has suggested. On lines 31 through 36, we parse the response from the actual API. Now, the API response could be a string or a dictionary or some other kind of object. We just handle all of the cases here. On lines 32 and 34, you can see that I just accessed the first 5,000 characters of the response. And on line 39, we print out the function API response. However, remember that we'd like the actual response to the user to be in natural language. And that's why on lines 43 through 48, we make another call to the model. I call chat.sendMessage, and we send the real response from the API to the model along with the function name. And this will allow the model to parse the API response and give you back a response in natural language. This else here is if no function call has been defined in the response, or if we are not aware of the function that the model asks us to invoke. Well, we set function calling in process to false, and then finally, we display the final natural language response from the model on lines 52 and 53. This will occur after the last function has been invoked. We are now ready to try this out. Let's send a chat message. I'm looking for some fun music events in the UK. And let's take a look at the response. We have the original prompt that we sent the model. The model identified search events as the right function to call with country code UK and keyword music. We then made a call to the actual Ticketmaster API and got this JSON in the response. We passed the JSON response to the model and we got this natural language response here at the bottom. Sabrina Carpenter is playing in Greenwich, London. These are live events, so it's quite possible that when you're running this code, the event that you see will be different. Let's try a different prompt. I'd like to attend a sports event in Canada. Here is the original prompt. Notice search events was the identified function to call. Here are the function parameters that the model suggested. Country code CA, keyword sports. Here is the API response from the actual Ticketmaster API. We sent this API response back to the model and we got a natural language response, which is printed here at the bottom. And you can see there are a number of sports events that you could attend. Now let's try something different. Could you suggest a concert venue in the UK? Live music, please. Notice now that the function to call is different. It's the search venues function. The parameters the model has identified are city London and country code UK. We have the actual API response from Ticketmaster and the natural language response at the bottom. The O2 Arena in Greenwich is a concert venue. Clearly, it doesn't know about the live music. It hasn't said anything. Let's try one more. How about a live music event in Paris? Please suggest venues. The model has identified search venues as the function to call with city Paris and country code FR. We have the actual API response from the Ticketmaster API, and here you can see the natural language response again from our model. The model gave us this response after parsing the truncated API response that we sent it. One last prompt before we move on. I'd like to explore museums in Rome. Do you have any suggestions? Now, the function to call will be different. Notice it now calls the search attractions function. The model has identified city as Rome, country code as IT or Italy, keyword museum. Here is the actual API response, and the model suggests the balloon museum and the design museum in Rome. Large language models like Gemini have a bunch of built-in knowledge. However, that knowledge is generic and maybe not specific to a particular domain or a particular use case. These large language models have been trained on data that is available on the internet. This means that they're unlikely to know anything specific about how things are done in your organization or how to solve for the problems that you have in your use case. Organizations have found that it's extremely important for these models to work with their own custom proprietary data. And in this video, we'll discuss how you can optimize Gemini models to work with custom data. Let me show you an example of why exactly this is relevant. Let's say you're working with a Gemini model that hasn't been optimized to your domain or use case. Now, you might ask the model something like, what are the best practices for preparing a statement of work? Now, a statement of work or a SOW can pertain to practically anything. And really, the prompt doesn't say what domain, what use case. Am I in construction? Am I in IT services? Or is it a statement of work for manufacturing? Now, the model tries the best it can from what it knows of the world. So it might say something like best practices include being clear about deliverables, timelines, and roles, ensure alignment with stakeholders, and use a standard template. Useful, kind of generic. But let's say you had a model that's optimized on your custom data. Maybe you're in the IT field and your organization has a set of rules and best practices to follow while sending a statement of work. Observe the response from the model. This has been optimized on your custom data. The statement of work should define system requirements, integration milestones, data migration protocols, and testing phases. Specify acceptance criteria for each deliverable and align with client SLAs. This response is perfect because the model incorporates industry-specific terms and focuses on relevant details, making it directly applicable to the IT consulting domain. Now, how do you optimize your model on custom data? There are three ways that we're going to be discussing. The first is grounding. Grounding ensures that the outputs of a large language model are anchored to specific reliable data sources. These data sources can be proprietary documents or databases, or even just Google search. This improves the factual accuracy and reduces model hallucinations. Another technique is to use the RAG engine. The Retrieval Augmented Generation or RAG engine enhances LLM responses by retrieving relevant context from external knowledge sources like vector databases and then incorporating this information into the model's response. And a third technique to incorporate custom data into a model is fine tuning. This involves training a pre existing LLM on domain specific data or tasks allowing it to adapt to specialized requirements and generate more accurate and context aware responses for a particular use case. We'll discuss all three techniques in more detail, starting with grounding. Grounding involves integrating the model with trusted APIs, proprietary databases, or live data streams, allowing it to fetch specific and accurate information as needed. Unlike static pre trained models, grounded models can adapt to changes in real time data because they are making use of these external live sources. This makes them ideal for tasks requiring up to date information such as market trends or news summaries. Gemini models can evaluate whether a prompt requires up to date or specialized information, and it can activate grounding selectively. If the model's existing knowledge suffices, grounding is bypassed. Otherwise, it retrieves data from sources like Google search or your proprietary database. Here are some of the benefits of grounding. By anchoring responses to real world information, grounding minimizes the likelihood of the model generating fabricated or unsupported content, usually referred to as hallucinations. Grounded models can retrieve and incorporate real time information, ensuring relevance in rapidly changing contexts, such as current events or market trends. By leveraging trusted sources, this improves the user's confidence in the AI outputs. This is particularly critical in sensitive domains like healthcare or finance. Grounding allows models to be tailored to specific industries by connecting them to specialized databases or proprietary knowledge systems. Here is a visualization of how grounding works with Gemini models. And this example shows you how a model can be grounded using Google search. But basically, grounding to any other data source follows a similar process. When you use grounding with Google search, it essentially links the Google model to the internet. The internet basically has access to existing and new information, so a grounded prompt can give you nuanced and specific prompt responses with little errors and with sources cited. Let's break this down. The user or the partner sends a prompt to Vertex. The prompt is the user message. That's the query that the client has. When your model is grounded using Google search, Vertex AI will consult Google search before returning a response to the client. So the Gemini model on Vertex AI will perform Google search and it will combine the power of Gemini and Google search to give you the response. When the response comes back to the user, it is a grounded response. It will cite sources and facts from the Google search that it has performed. So, not only do you get the text response from the model, you'll also get citation sources from the model. The model will tell you where it got its information from. And in addition, it can also provide you with search suggestions. Now, Gemini models need not always use grounded sources for its response. It has the ability to selectively activate grounding. The system will evaluate whether a prompt requires up to date or specialized information. If the model's existing knowledge suffices, grounding is bypassed. Otherwise, it will retrieve the data from grounded sources such as Google search. By dynamically deciding when to perform grounding, the system balances response quality with operational efficiency, reducing unnecessary data retrieval and the associated costs. Developers can set thresholds that determine the conditions under which dynamic retrieval activates, tailoring the system's behavior to specific application requirements. When you ground to your proprietary organization data, you'll make use of Vertex AI data stores, which are an important component in the Vertex AI Agent Builder. The Agent Builder service enables you to create AI powered conversational agents tailored to your organization's needs. Data stores act as the knowledge base for agents, storing the structured and unstructured data that they rely on to provide accurate answers. Data stores allow you to incorporate various data types such as website content, unstructured documents, and structured records into your AI applications. This integration ensures that LLMs have access to the most relevant and up to date information specific to your organization. By grounding LLM outputs to these proprietary sources stored within these data stores, models can produce more precise and contextually relevant responses, reducing the likelihood of generating incorrect or fabricated information. These data sources act as sources of proprietary information not only for grounding but also for RAGs or retrieval augmented generation. Here are some common sources that you can use to ground Gemini models. This is not an exhaustive list. Other sources are also supported, but this will give you an idea of what some common sources are. Gemini can integrate with search engines like Google to allow it to fetch real time, publicly available information for a wide range of queries. Gemini can connect to proprietary databases and thus have access to internal company databases to provide domain specific, highly reliable data for specialized applications. Information such as product catalogs, financial records. Gemini can connect to knowledge graphs. Sources like Google Knowledge Graph or Wikidata offer structured, well organized facts and relationships for contextual understanding. Gemini can connect to APIs for real time data. APIs such as those for stock market data, weather updates, or sports scores allow the model to retrieve dynamic and time sensitive information. Gemini can connect to scientific and academic repositories such as PubMed or Archive to give it access to peer reviewed research, ensuring credibility for scientific or technical queries. Another useful source is for personalized applications. You can ground with customer data systems such as CRM systems or customer data platforms that help tailor responses to individual user profiles or histories. In this demo, we'll see how you can ground the responses that you get from Gemini models. Grounding is the ability to connect the model output to verifiable sources of information. If you provide your model with access to specific data sources, then that grounding tethers their output to this data and reduces the chances of the model inventing or hallucinating content. Grounding is extremely important in situations where accuracy and reliability of the model are significant. Let's say your organization has a large amount of internal data that they've collected over time, and you want your model results to be based on this factual data. What you do is ground your model results to this data so that the model responses are anchored to this specific information. Vertex AI allows you to ground supported output in two main ways. You can ground to Google search results or you can ground to your own data. And we'll show you both here in this demo. Let's get started. Set up the imports that you need. I'll explain the different classes that we use as and when we use them. Once again, we'll initialize our Python SDK and now we are ready to get going. Now the model that I'm going to use is the Gemini 1.5 Flash model. When we enable grounding for our model, when we get our model response, we'll also get citation links to the original source from where the model got the response. Citation source links are usually numbered, and it would be nice to have superscripts next to each bullet point of text generated with a number referencing what source that particular bit of text came from. This is just a helper display function and has nothing to do with actually configuring grounding for your model. Now, Google has provided an example notebook with just such a helper function. And that method here is called print grounding response. And I basically just got this helper method from this Google example notebook on GitHub. Now I have to admit that I simplified this code just a little bit and I had to make a few tweaks in order to have it work properly in my notebook. Since this doesn't have anything to do with the actual grounding of the model, I'll quickly run through this code. Now the input argument here is the response from the model, the generation response. On line 3, we access the grounding metadata. On line 7, we encode the response using UTF-8 encoding. Then on line 15, we run a for loop over the grounding supports, which gives us access to the text segments that the model attributes to certain grounding sources, either web search or private data. The code on lines 16 through 26 is basically getting access to each text segment and then using a superscript index to point to the right grounding footnote. The code on lines 37 through 43 parses the grounding metadata that was retrieved. These are the original sources that the model has used. The web search queries are in a different section. We parse those differently. And the retrieval queries are in a different section. And then the code here at the bottom, the for loop on lines 48 through 55, this iterates through each grounding chunk and prints out a list of citation sources at the very end. The citation sources are all numbered using the index, and they include the context title and the context URI. And finally, on line 58, we display the parsed markdown result. In our first example, we'll see how we can use grounding with Google search. This will link the Gemini model to the internet. Non-grounded generative AI model responses do not give you factual content that are time specific, something that happened yesterday or 1 month ago. Since the internet gives us access to existing and new information, up-to-date information, a grounded prompt can give you nuanced and specific prompt responses with little error and with its sources cited. Here is our example prompt. What is the release date for the next iPhone model and what new features can we expect? Now, when I'm recording, the next iPhone model is almost a year away. Let's see what the model has to say. I'm going to call model.generate content, but I haven't specified any grounding sources. We've seen the basic structure of the model response with the text and the additional metadata. Let's parse just the text and display that. You can see that without grounding, the model tells us that it does not have access to real-time information, including future product releases, and it gives us some sources that we can maybe explore to get this information. Now let's enable grounding. You can ground model responses using external tools. On line 1, I call tool from Google Search Retrieval and pass in grounding.google search retrieval to connect our model's response to Google search. Now when I call model.generate content, I pass in the original prompt on line 4. On line 5, I connect this grounding tool. In addition, because I'm looking for factual responses, I set the temperature in the generation config to 0 so that the model is as deterministic as possible when it gives its response. Now let's look at the structure of the response. Now, even though I'm recording this when iPhone 16 has been launched, the model's response tells me that the iPhone 15 is the latest iPhone released on September 22nd, 2023. So clearly the model has not got this perfectly right, but at least it gives you a response. I tried to figure out why exactly the model got wrong, and I found the answer here in the grounding metadata. Notice the web search query, it says iPhone 15 new features, iPhone 15 release date. So for some reason, the model felt that the iPhone 15 was the latest iPhone and it made a very specific search for iPhone 15, and that's why we got the wrong response. Just a little warning for all of us that generative AI models can get things wrong even with grounding. Let's print out the nicely formatted grounding response. And here you can see Gemini's response. Observe that next to each sentence, we have a reference link. Next to the first sentence, the reference links are 1 and 2. Next to the second sentence, 3. And next to the third sentence, 3. These correspond to the grounding chunks at the bottom. Here in grounding sources, you can see the search queries that were made to get these results and the citation sources in grounding chunks. These were the 3 sources that the model made use of Mac Rumors, YouTube, and Reddit.com in order to give us our response. Let's open up one of these and you can see that this likely talks about the iPhone 15. We got the wrong answer, but we have the citation sources for the model's response. If you go to another source that it has cited, reddit.com, you can see that this talks about the iPhone 15 as well. It talks about iPhone 15 features. Well, the model did so in the previous response, not really what we wanted. But here is another example where the model does very well. My prompt is, can you give me a summary of NVIDIA's and Meta's latest results? This is not something that a non-grounded model could answer. On line 3, I pass in the Google Search Retrieval tool. And again, we'll set temperature to 0 so that the model's answers are at its most deterministic. And we'll print out the grounding response. And you can see that it correctly identifies NVIDIA's latest results, third quarter fiscal 2025. This is how NVIDIA refers to their results. And then you have Meta's third quarter 2024. That's again the current year. Remember, that's the fiscal year and this is just the year. So grounding has given us the right results here. And then of course we have the references. You can see the web search queries were Meta results, NVIDIA results. The cool thing is because these sources are available, you can actually verify against these sources. Here on nvidia.com, here are the latest results for NVIDIA. And if you go to this last link here on q4cdn.com, you can see that we get Meta Platform's latest results. Grounding has its own pitfalls, so again, you have to be careful with the results. You should know though that overall, grounding greatly mitigates hallucinations in the model and allows you to get time sensitive results in natural language. In this demo, we'll see how you can ground your Gemini language model to your own text data. At the time of this recording, this feature is currently in preview. You can store the data which you want to use to ground your model in a data store within the Vertex AI Agent Builder. Vertex AI Agent Builder is the platform that provides a user-friendly interface and tools to design conversation flows, integrate with backend systems, and customize AI's behavior. The data store is basically the store of data where the agent's knowledge comes from. This is the data store that we'll use as the source of truth for our model's responses. Our model's responses will be grounded using the content in this data store. I have a PDF file here on my local machine, which is the customer service manual for this fictitious company called Quick Bite Food Delivery. This is essentially a bunch of instructions that I had a generative model generate for me, assuming that these are what customer service agents for this company have to follow. You can see that we have a table of contents. This is a fairly long document. There are a total of 9 pages here. Now we have just one document. This is going to be our source of truth for the model's responses. But you can imagine in an organization that there are likely to be many such documents. In order to be able to use the agent builder and ground your models to your personal data, make sure that the Vertex AI API is enabled. Now we enable this API the first thing here in this learning path. So this should still be enabled, but it doesn't hurt to double check. Next, I'm going to head over to cloud storage and create a new bucket to work with the grounding functionality and in the next demo, the RAG functionality. So we'll use the same bucket for both. Now, the reason I'm creating a new bucket is because the bucket needs to be configured with some specific features so that the data store can directly access the contents of the bucket without you having to set up any additional permissions. I'll point out what those features are. The first thing, you need to pick a globally unique name for the bucket. I'm going to call this the Looney Rag Grounding Bucket. Let's continue. Let's store this bucket in a single region and I'll place this in US Central 1 because that's where we are using the Vertex AI APIs. Hit continue. The next thing to specify is the storage class for your bucket. Go with the default standard storage. This is meant for data that is frequently accessed. Now here is where the difference is. Make sure that your bucket access control is set to uniform and ensure that you enforce public access prevention on this bucket. If you change these default values, so for example, if you choose to go with fine-grained access control, you'll have to set up additional permissions for the data store in the agent builder to access the data here in this cloud storage bucket. So please make sure that you set these two settings to the default values and don't make any changes in order to perform the remaining steps seamlessly. Next, you can go ahead and uncheck the soft delete policy so that older versions of your data are not kept around. This is Google's recommendation. Go ahead and create the bucket. This is the bucket that we'll use for our grounding sources as well as for the RAGs demo coming up after grounding. Now in this bucket, I've created a folder called grounding. I won't show you the folder creation since you're familiar with this. And if you click through to grounding, you'll see that I've uploaded the PDF from my local machine, the customer service manual for Quick Bite Food Delivery platform. Now we are going to need the gsutil URI for this PDF file. So go ahead and copy it and save it somewhere. We'll be using it in just a bit. Now we need to head over to the agent builder. This is the platform that Google offers for conversational AI applications like chatbots or virtual assistants. If you're accessing the agent builder for the very first time, you'll need to enable and activate the API to use the agent builder. You'll see a big blue button on screen asking you to activate the API. Click on that button and follow through with the steps that are needed. Activating this API will set up a service account used by the agent builder, and this service account will automatically have the permissions to access your cloud storage buckets. So when we store our private data in cloud storage, the data store that we create here in the agent builder should be able to access that data directly without you having to specify any additional permissions. This platform allows you to build these apps without needing to be a machine learning expert. Now, the private data that we'll use to ground our model responses will be stored in this data store. Just a heads up here, make sure that you're creating your data store and app in the same project where you're going to be using the Vertex AI APIs. Notice on the top left, I'm in the same GCP LLMs project. This data store will serve as a knowledge base for our model. This is where we can upload text documents and product catalogs and any other private data that we have within our organization. Let's go ahead and create a data store and connect it to the cloud storage bucket where our data is stored. Observe that our data store can connect to many different data sources. It can index your website, access BigQuery, connect to your API, connect to your Gmail or Google Drive. We'll go with the simplest of all, cloud storage, because that's where we've uploaded our PDF file. Go ahead and select that. Next, you'll need to specify what kind of data you're importing. The default selection here is correct for us, unstructured documents. Ours is a PDF document after all, but you can see the other types of data that are supported. Next, we have the synchronization frequency. You can periodically ingest data from this source, or you can go with one-time ingestion. We'll stick with the one-time ingestion. Next, you can specify the folder where your data lives or just point to a specific file. Since I have just one file, I'm going to select the file option. And you can just paste in the gsutil URI, or let me browse and show you how you can select the specific file that you'd like to use as your grounding source. So in the grounding subfolder, I have my quick bite food delivery platform customer service manual. I'm going to go ahead and select that. And this should be accessible. Notice the check mark showing you that this data store can access your cloud storage bucket files. If you had not set up the bucket exactly how we did earlier in this video, you'll find that the file may not be accessible by default. You can now hit continue. Let's move on with the other configuration. Here you can specify where your data ought to be located. It's better to go with the global configuration so your data is accessible from anywhere. But if for compliance reasons you need to place your data in a certain location, you can configure that here. Next, you'll need to specify a unique name for your data store. I've just called it grounding quick byte. We can now accept the default values for everything else. Go ahead and create this data store. This data store will take a few minutes to be created and for your documents to be indexed. Make sure you copy over the ID that has been generated for your data store. We are going to be using this in our notebook. Now let's click through to the data store to see whether it has been set up. You can see that the Documents tab is currently empty. That's because data is still being processed and no documents are indexed yet. Let's head over to the activity and take a look. Notice that import was in the process, but now it's completed. It seems like the documents were imported successfully. Let's head back to the document section. And here, if you were to now hit refresh, the documents that were indexed should show up here on screen. It seems like our data store has successfully connected to cloud storage and has indexed the document that we need to use as our grounding source of truth. The next thing we'll do here is create a search application connected to the data store that we just set up. Click on Create New App and you can see all of the different types of apps that you can build. We'll just build a simple search app. So scroll to the top. What we want to be able to do is document search. So go ahead and create a document search app. You can leave all the features checked. We want enterprise edition features, advanced LLM features. Let's give our app a name, Quick Byte Search App. You can specify the external name of your company or organization. I'm just going to say Quick Byte, and our app is going to be located in a multi-regional global location. You can just leave all of these default values. Click on continue. This is where you pick the data store to connect to your search app. We have our existing data store here, grounding QuickByte. I'm just going to select that and I'm going to hit create to create the search application. We are now all set up to connect our private data to the model response. Under the documents for the app, you can see that our customer service manual has been indexed. If you head over to activity, you can see that the import of the data from the data store was completed and the schema was updated as well. We are now all set. Let's head back to our notebook and see how we can ground model responses to our own data. So we set up the data store project ID. Our data store is in the same project as where we are using the Vertex AI APIs. This is important to remember. We've set our data store up correctly, so we should be fine. Next, the location of our data store, we have the location set to global because that's what we had configured when we had set up the data store and app. And then we set the data store ID that we copied over from the cloud console. Next, let's set up the prompt that we're going to be asking our model. What should you do if a customer makes a request to modify their order after it has been placed? What I'm going to do is ask the model to respond without specifying any grounding sources. Observe here that I call model.generate content, pass in the prompt, but I haven't specified any grounding sources, and you can see the model basically gives me a common sense answer. It's giving me a very detailed, sensible sounding answer, but this is a very general answer and is not from the customer service manual because I haven't provided that as a grounding source. Let's point to the data store and the Vertex AI app that we've created as a grounding source. I instantiate the tool on lines 1 through 9, tool.fromRetrieval, and then in the preview grounding library, I instantiate the retrieval object, and our grounding is via Vertex AI Search. It's a search app that we have set up after all. Vertex AI Search takes in the parameters of the data store ID, the project, and the location. And then when we call model.generate content, pass in these tools as an input argument. And we'll print out the model's response with grounding data. Observe the response is shorter and it's directly from the customer service manual. You can open up the manual and verify if you want to. But the model got it right. And notice the only reference here at the bottom, that's our own private grounding source. So far, all of the grounding examples have used free form mode, where conversation history is not stored. However, it's possible to ground your model responses in chat mode as well. And that's what we look at here in this video. The same two grounding sources, Google search results and your private data, can be used as grounding sources with the model in chat mode. Now I'm going to set up two prompts, the original prompt and a follow-up. The first question is about the Internet of Things, and the second question is about how is this used in smart homes. We'll now interact with the model in chat mode and we'll use Google search as the grounding source. On line 1, we use the tool.from Google search retrieval function in order to set up Google search as a grounding source. On line 3, we start the chat session. On lines 5 through 11, I call chat.sendMessage to send the first message to the chat. Along with my prompt, I specify the grounding tool on line 7 and I set the temperature to 0 so that the model gives me deterministic responses using the grounding source. Let's print the response from the model, and here you can see it describes IoT, and then of course it has those little reference links, and you can see all of the sources that it has looked at in order to give you the natural language response. Those are the 4 grounding chunks. Since this is a chat session, we can follow up with another prompt. I pass in my prompt follow up. Again, I connect up Google search as a grounding tool and leave the temperature as 0. And I get a response to my follow up prompt, again grounded in fact from web pages that Google search has found on the internet. Since we have our search app and data store set up already, let's use our private data as the grounding source. Here is my prompt and my follow-up. First, what are the steps to take when handling a customer complaint about the quality of food? And then I have a follow-up. How do you offer a resolution or compensation to the customer? We start our new chat session on line 1. On lines 3 through 11, we set up Vertex AI Search as the grounding source. Vertex AI search points to our data store. You can see the configuration on lines 6 through 8. And when I call chat.sendMessage, I specify the prompt, I connect up the grounding source tool, and then I set the temperature to 0. Let's take a look at the response from the model. You can see that the response is directly from the customer service manual PDF. There's exactly one reference source at the bottom, and that's our manual that has been indexed by the agent builder data store. Let's send the chat session our follow-up prompt, chat.send message with the prompt follow-up. Again, I connect up the grounding tool. Now I haven't specified temperature 0. Your model's response will still be grounded on your private data, but it's generally good practice to set temperature to 0 when you're using a grounding source. And here is the model response grounded in our customer service manual instructions. Now, since we are done with this app and this data store, let's go ahead and delete it from Cloud Console. I'll show you how you can follow Google recommended best practices to delete the app and the data store. Now, here I am on Agent Builder. The first thing I'm going to do is purge the data from the data store. So head over to Data Stores, click through to the grounding quick byte data store that we had set up earlier, and notice under Documents, you have an option to purge data. Before I actually purge this data, let's head over to the Activity tab, and you can see the only activities on this data store so far have been import completed and then schema update completed. Now we'll go back to the documents and click on Purge Data. This will delink the data store from the cloud storage bucket where our PDF file is stored. So go ahead and confirm the purge of this data. And once you hit confirm, in a few moments, you'll find that the data here has disappeared. While we wait for this data link to disappear, let's head over to Activity. And here you can see that the purge is now completed. It's been about a minute since I purged the data, so I'm going to head back to Documents, and here I'll find that the data has indeed disappeared. Now, let's head over to the data store and try and delete that. You'll find when you click on the three-dot menu, the delete option is disabled. That's because there are applications that are connected to this data store. You have to delete the app first. So head over to Apps, and there is a Quick Byte Search app. You can see the connected data store, the grounding Quick Byte data store. Let's go ahead and click on the three dots and delete this application. Once you confirm the deletion of this application, there is no app referencing our data store, which means we are free to delete the data store next. So confirm the deletion of the application and now head over to data store and delete the data store itself. Once again, click on the three dots. The delete is now enabled. Click on delete and paste in the name of the data store to confirm deletion and go ahead and hit confirm. At this point, we've deleted all of the resources that we created in this demo.